Thank you so much, and it's lovely to be here. Can everybody hear me? Okay, awesome. So today I wanted to talk about what AI's next frontier would be, which, in my humble opinion, is neuromorphic computing. And I'll try to motivate this talk as to why, as we are moving along this path towards artificial intelligence, why we need to consider hardware more closely, and why we need to especially take more inspiration from each of our brains. So before that, just very quickly, I'm a principal member of technical staff at Sandia National Labs. I work as part of the Center for Computing Research, and I specifically, my department is called Cognitive and Emerging Computing. So we're really looking forward to what's the next generation of computers going to look like. All right, so I talked about the next frontier for AI. And so first I want to motivate why this is a problem. So if we look at energy consumption for modern AI systems, and sorry I don't have my clicker, but this is just based on data that we have that's currently published. We only have data until GPT-3. No data was, or stats were published for GPT-4. We have a general idea where the trends would be going. So with GPT-3, in terms of number of parameters for a model, which in this case would be the trained synaptic weights for a large language model, there are about 175 billion parameters for GPT-3. And the energy consumption is about 1 million kilowatt hours. Now for context, that's what a big city like Miami would consume in terms of energy in a month. Right? So that's what training GPT-3 would take. And where GPT-4 is even further above, right? So it's estimated to have about 1 trillion parameters. And we don't have any energy numbers, but you can imagine it's somewhere along that curve that I'm showing. Now, I did a calculation for humans over our lifetime. And this was not just isolating the brain's power, but just the energy your body would require every day for an average lifespan of a human in the US. And if we're assuming that the human brain has about 1,000 trillion parameters in terms of synaptic weight, for humans, we take over our entire lifetime an order or 2 orders of magnitude less energy than it would take GPT-3, which is a large language model for training. And that's important because that's humans for their whole life. So just training over their 70, 80 years, if you will. And so why that is important is because we're still on this trajectory in terms of building larger and larger systems like GPT-4, which is untenable in terms of power consumption. We can't keep on building larger and larger systems. And now it's to the point that only very few large companies can afford to train and build these kinds of models. And not only that, Google and Microsoft are talking about their nuclear power plants, right? So the issue with where computing is going currently is just it's not feasible with where we want to go. And so what I want to argue today is neuromorphic computing, which is essentially brain-inspired computing, is a path forward to meet these computing needs that we want in the future while also giving us the performance and efficiency that we want. All right, so dialing it back a little bit. So what does a modern computing landscape look like today? Most of the computers that you see today are digital in nature, whether it's your CPUs, your GPUs, FPGAs, which are field programmable digital arrays. They're discrete valued, they're deterministic, they have higher precision. And I would say they have simpler building blocks. So you have a basic set of logic blocks and you can build more complex functions out of it. Now, if you look at more analog computing, the brain's a great example of that. It's continuous valued, it's stochastic. It has lower precision, but the building blocks themselves can be a lot more complex. For example, neurons can be very complex. What I would argue is we also have a lot of analog computing research that would fall under this group too. And in fact, neuromorphic computing saw its genesis in trying to capture some of the analog properties that you see in the brain in silicon. So what do I mean by this complexity I just talked about? So if you look at the simple, I guess, the perceptron model that most AI machine learning models will use today, it's basically a weighted sum of your inputs, and then you apply an activation function on that. So that's inspired basically from the perceptron model, and this was, early, or I guess late 1940s or so when this model came out. And now with a lot of neuromorphic systems, you can say add more complexity to what your Soma does. So you might have a leaky integrated fire. So you have another leak function maybe added to the neuron. And if you wanted even more biological realism, you might maybe have a Hodgkin-Huxley model to capture what the Soma does. But what about all the other factors that go into a neuron? Like you have dendrites, you might have different kinds of synapses. That's why I have a biological neuron right up top, and that's like a L5 pyramidal neuron in the human brain. But it looks a lot more complex in these simplistic representations. So one thing that I would bring to the fore is our model of a neuron that we're using in our AI machine learning models is very simplistic and very homogeneous today. So what exactly does neuromorphic computing want to do? Essentially, neuromorphic computing wants to capture the same things that our brain does, which is learn ill-structured problems, deal with noise easily, have redundancy baked in a way that it doesn't just throw off your answers, do transfer learning. So for example, if you've learned a particular task, and if there's a similar task to it, you don't need to be trained all over again on it, because humans do it with fewer, I would say, samples. They learn a new task. So that's the functionality we want to capture. But the attributes that we want to see is we want computation and memory to not have a lot of separation. So most of computers today have a von Neumann architecture where memory is separate, computing is separate, and there's a lot of interchange of information between them, and that can also be very expensive. So we don't want that. We want the same components to be able to be non-volatile, have memory, and also do computing. We also want more complexity per a single unit. So like I was talking about in the previous slide, we don't just want a very simplistic representation of a neuron. We need more complexity in a single neuron. A lot of neuromorphic computing that I think is prevalent today, you'll see a lot of spiking and event-driven communication, but there's a lot of processing that happens even before a spike occurs. So subthreshold computation that we see in brains, how do we capture that in hardware? And then also using stochasticity as a feature. So noise is inherent in the system. How do we actually leverage it for computation, or how do we account for it in our algorithms? We're not going to have high precision all the time. And then, of course, we have more dense local connectivity and massively parallel computation. So these are things that we really want to capture in neuromorphic computing hardware. And the goal here, again, is to try to get to where a single neuron go. And there's this good paper by Jen Hassler in 2016, which shows like an average CPU would consume 1 million multiply accumulates. So you're multiplying and you're doing an accumulation or an adding operation per second per milliwatt for an average CPU. And a single neuron would be capable of doing 1 million Mach per second per picowatt. So about 9 orders of magnitude difference. And so that's what we really want to capture in our hardware today. So what about neuromorphic approaches that exist today? You'd be happy to know there's already a lot of work that has started in this field. I would still say more needs to be done. But there are 3 different approaches currently to neuromorphic computing. There's a purely digital approach, and this is built off of CPUs, neural processing units. Neural processing units, you can just think of these as really fast matrix multiply units that you have even in your Apple processors today. But digital neuromorphic systems have been scaled to about 1.15 billion and about 2 billion neurons. And I'll show you guys a snapshot of the 1.15 billion system. It's Intel's neuromorphic system that actually is hosted at Sandia. And in this kind of system, it's still deterministic. It is higher precision. But moving on to more analog and mixed signal approaches, because this is where we're really embracing even the analog nature of hardware. Because believe it or not, transistors are not just switches, they also have analog behavior, and there are systems that actually capture that. These analog mixed signal systems have been scaled to about 1 million. They're analog and have stochastic behavior, and they typically have lower precision. And then there's also beyond CMOS, which is looking at new kinds of devices and materials beyond transistors that we use today. And especially looking at ways to integrate them easily with CMOS in order to build systems that are, that give us memory for cheap, that give us certain kind of biological behaviors for cheap that we don't have today. All right, so I would say neuromorphic computing offers a lot of computational richness. So a lot in the field today is focused on in-memory computing, especially with synapses. So you'll see a lot about cross-bar architectures or these neural processing units, because everything in terms of algorithms today is kind of geared towards feeding multiplication and accumulation, our MAC operation. But there's also other features that are pretty important. And let me see if I can get this video to go. Apparently not. So this is a vision sensor. Essentially, this is a kind of image sensor that only captures when there is a change in the scene. So imagine, rather than actually recording a video where you're looking at every frame pixel by pixel, you have a sensor that only captures a change in the scene. And that's a neuromorphic sensor. It's inspired by the retina. It's called a silicon retina or an event sensor. And it's actually even been commercialized. So there are a bunch of companies like Prophecy that actually sell these sensors. So it's becoming more and more a reality, but there are challenges because you don't quite know how to use sensors. And in another sense, in terms of neural processing itself, and I'll delve into this in some more detail in my talk, is how do we make neurons more complex? And specifically, I would be talking today about dendrites, but there's also how do we incorporate learning more efficiently? How do you incorporate multimodal inputs into your models, your neural networks? And then how do you actually design these systems for all these varied applications? And all these applications shown here, from AI/ML to brain-inspired algorithms to scientific computing to edge computing or high-performance computing, are applications that people are actively trying to demonstrate the utility of neuromorphic computing for. All right, so I did promise the neuromorphic supercomputer, and this is the 1.15 billion neuron system we have at Sandia currently. It's a fully digital system. It does have a trillion synapses, and in terms of power consumption, it's about 2,600 watts. And it has about 8-bit precision. And currently, we're in the process of testing larger neural networks on it. So this is an example of a neuromorphic system that's been scaled up. But I would argue we need more from the hardware. So another example that I thought would be pretty useful to show would be the edge computing example. And again, I hope this video can run, which not me. Wow, that's a shame. Anyway, you'd have to imagine it's just, you can just see the little hand moving, and all you can see is the contour of the hand moving in the scene. And really, as you can see in this frame, there's obviously other things in this frame that are not being captured. But there are also these spurious events all over the place that you would know are not relevant compared to this guy here, where, I would think most of you would realize that's a sort of a fist or a hand. So this is an example of what the data from this kind of image sensor looks like. So hopefully this is a better illustration of it, which is the event sensor is capturing just the pedestrian. So you're seeing the scene, but it only has the contour of the pedestrian. And we used a spiking neural network to actually further remove more background information from the scene so that post-processing our algorithms could only focus on the pedestrian. So this is a classic case of especially when I'm driving. I don't want to be processing the images continuously. It can be very expensive. How do I specifically only annotate certain regions in the image that I care about? All right. So how could we use neuromorphic computing for AI performance? So essentially, as I was showing earlier in the graph, the pink box is where we are with conventional computing, conventional digital computing. To move towards neuromorphic computing, not only do we need to move away from how we design our computer architecture, but we also need to go closer to where brains are in terms of brain. And you don't just need scalability, which means a billion neurons alone are not going to get you there, but you also need complexity per neuron. You need to be able to tackle any noise or stochastic behavior you see in these systems. And specifically to design a system like this, you need to be able to do co-design, because algorithms and hardware cannot be sitting at two different ends and solving different problems, if you will. It needs a more concerted effort to come up with solutions. And in addition to that, another thing I would add is we need heterogeneous architectures. And so far in digital, we've been going with more homogeneous structures, and we want to improve that. All right, so in terms of neuromorphic systems, what I'm specifically very interested in studying are dendrites, and how do I actually capture these efficiently in hardware. And they're typically like over 70% of a neuron's volume, but they're really minimized to just wires when you're representing a neuron. And to me, it seems like dendrites have a lot of diversity in terms of how they connect. So they don't seem just like wires. And also, they seem to be incorporating some complex spatiotemporal pattern recognition or amplification of certain inputs, or integration in a way that might be helpful for computation. And specifically, if you're looking at spatiotemporal inputs as inputs are just streaming in, dendrites are a great way to find coincidence detection, to actually say that a certain pattern was detected or not. They can also perform nonlinear filtering. So, the activation function that you're thinking typically in a machine learning neuron model where you're just applying the activation function, dendrites can implement some nonlinear function before you even get to Suma. And selectively amplify or shunt certain inputs. So with that, essentially the architecture that I was interested in designing was not just the Soma, but a dendritic tree-like architecture around it. And believe it or not, this is simpler to do with transistors itself. So if you think of dendrites as a cable, and you can approximate a cable as a resistor, capacitor, delay line, you can use transistors to represent these. And in order to modulate more active properties, you can introduce active channels on that dendrite to further introduce functionality that you would not otherwise have in a passive cable. And I wanted to highlight that it's not just me that's been interested in looking at architectures like this. People have looked at nanodendrites, whether it's with ferroelectric FETs, the group from Stanford. They have a proposed 3D architecture that they want to build with dendrites. And also with memristors, people have looked at how do we incorporate dendrites to introduce delays, to introduce kind of the spatiotemporal functionality I was talking about in terms of processing sensory input. All right, so I wanted to focus on something simple. And I say it's simple because it's, at least for my neuroscience friends, it might seem pretty obvious. Was incorporating shunting inhibition in our circuit. And shunting inhibition, essentially, you can just think of it as gain modulation in this particular circuit, and a particular input here, in this case, the shunt input, can modulate the rest of the inputs that are coming into the dendritic line. And essentially, what we showed was in this transistor model, you could, if you're modeling the leakage with a transistor, you can modulate what a shunt would do in a biological system, thereby giving you this gain modulation that you see between the input and the output. And why would that be useful? So we actually took this and tried to create a direction selective circuit. So in this case, we had a dendrite that had a left to right preferred direction, and its strongest response was only when it was going in that preferred direction, and everywhere its response would be lower. And we demonstrated that using this circuit, and this model was, I believe, inspired by the fruit fly's T4 dendrite model that Groshner et al. Had published. And so this was interesting in terms of some biological data that's now being shown with circuits. All right. Going to next. So what next with this? I talked about event sensors earlier. What could dendrites like these do? Now imagine I had, and these are just transistor-based dendrite circuits. Imagine I had them sitting right next to the sensor, very quickly doing some pre-processing for a pattern that I was trying to find. If this was my large image sensor, and for every pixel I could very quickly give you features or patterns that I care about in that image, I would get a lot of information streamlined and out of this quickly. And that's the utility of a circuit like this, right next to a sensor. We also use this in a dragonfly interception model. So my colleague, Frances Chance, she has a dragonfly interception circuit, which is essentially like a 3-layer neural network. And what we did was we replaced the hidden layer of neurons with these sensory motor dendrites, I would call them, which are essentially integrating the information from the retina and the fovea. Fovea is essentially just telling you where you are in the scene. And basically, the dendrites were not only able to do the multiplication that is needed, we were also able to prune the connections so that we did not need all-to-all connectivity that we needed in this network before. So that was another example of us showing that we could get essentially similar performance for what we did with that original neural network, but with dendrites, we were able to do it more efficiently. And the key here is you're not implementing full neurons. Dendrites are a lot cheaper to implement in hardware than a full neuron model. All right, and so this is talking about AI's next frontier. So we actually took a regular AI model or machine learning model that would actually capture what a nonlinear function would look like. And what we did was, and I'll try to walk you through this experiment a little bit. Again, it's a smaller neural network, but what we have is we have leaky integrated fire neurons as the hidden layer. So we had about 256 hidden leaky integrated fire neurons. And what we did was we replaced that with 16 neurons, 16 leaky integrated fire neurons that actually had dendrites. So it's a multi-compartment neuron with dendrites that we're replacing instead of using 256. And we showed that we were getting a lower error in mapping a nonlinear function using these fewer number of neurons. So this goes to my earlier comment of if we simplify our neuron models too much, it's probably why we need a lot of them. But if our neuron models are more complex, we can more efficiently map them into neural networks. And not only that, our neural network would be smaller, which is exactly what we want for energy efficiency as well. So we took this, and in this case, we haven't replaced it in all parts of this ResNet network, but my postdoc was able to show, just by replacing the pooling layer, where dendrites are just aggregating information from all the layers ahead, that it was orders of magnitude better than what a GPU implementation for that pooling layer would be. So as you can see, for the NVIDIA Jetson, it was about 500 microjoules, and using our analog hardware-based generative pooling, it was about 0.2 microjoules. So a big difference in terms of energy or comparable accuracy. And so what we've actually done is we have created, and I keep forgetting what we're calling this piece of software, but we have actually released the software. So this is available if you're ever playing with PyTorch or SNN Torch and you're interested in spiking neural networks. You can actually go find this dendrite model and use it for however you're building, whatever neural network you're building, this is available. I don't have the link for it, but feel free to reach out to me if you want to see the open source code for that. All right, so far I talked about taking inspiration from biology, including dendrites in hardware, and actually now incorporating them into neural networks. But how do we kind of go about this whole thing? And I would say it was pretty challenging because it not only needs you to understand algorithms and applications, it needs you have to understand what the system architecture is, all the way to circuits and systems and down to what if you're using new materials or devices. And so this takes co-designing, which is very challenging, especially since it's across many different fields. And I would argue tools are very important. So what we started off with was trying to come up with a tool called Athena that would be able to capture neuromorphic accelerators, more specifically for any kind of neural network design that was released. And we didn't quite limit it to spiking, but it can also do spiking neural networks. And what we did was we can take any description, whether it's in PyTorch, Keras, what have you, and map it onto Athena, which would be based off a neuromorphic accelerator, and then it would spit out results just like it would if you were targeting this onto a CPU or a GPU. And the advantage of doing something like that is I can easily now across different neural network types. In this case, we're looking at ShuffleNet, AlexNet, and DenseNet, and Inception V3. We can compare different architectures. So this is another open source tool that Sandia created that can actually help you compare different kinds of neuromorphic architectures, because even in the neuromorphic field, there's a lot of diversity currently in terms of how different circuits and architectures are implemented. All right, but specifically, even though we had Athena, that did not quite address how we would build neuromorphic architectures per se, because AI and machine learning is specifically mostly geared towards doing very fast multiply accumulates, and we wanted to go beyond that. And in this case, how would you define a neuromorphic architecture that has, n number of neurons? Each neuron maybe has m number of synapses, or how many ever dendritic stages. Perhaps it has branching. And so we actually created a neuromorphic simulator in collaboration with UT Austin. And this was part of an internal lab-directed research or development program called an LDRD at Sandia. And essentially, the idea was create a simulator that can abstract out all these costs, right? Whether it's what's the cost for spiking, modeling any functional behavior, tracking performance, how are messages shared intra-core and intercore, and calibrated. So what we did was we captured Loihi's numbers, and we did it for an application for gesture recognition using an event sensor camera. And basically what we saw in this simulator is we got pretty close to what the hardware energy and latency predictions were in this software. So what's the advantage of doing something like that? And this is just another example of the devious gesture shown in more detail. The advantage is that Loihi, which is Intel makes this neuromorphic chip, comes with a very specific configuration, how many ever neurons, how many ever cores it has. And essentially we use this simulator to find the optimal number of neurons per core, how many cores would you have. And it had a different number in terms of optimizing for both energy and latency, as shown highlighted here, than what typically comes with the system. And so that was interesting to see. We saw that with about 170 cores, it would be about 21% faster. So this is why design space exploration is important, because you can find new architectures that might actually work better for the hardware you're trying to design. This was another very famous neuromorphic chip called IBM's True North. It was actually the first digital chip that went to 1 million neurons. And this was, again, us comparing the Santa Fe simulator to NeMo, which is a high-performance computing simulator. And this is just showing that Santa Fe is really fast, and was done in the fraction of a time that NeMo took. And mainly the idea here is we're abstracting well enough, and it's also C and C++ code, which is a lot faster. All right, so if you're interested in exploring more dendrites in the Santa Fe hardware simulator, I do have a QR code for this, so feel free to download it and test it out. We're always happy to hear feedback, especially because one of the reasons I feel machine learning has taken off so much is we've had more open source designs and more community input, and that's what we also need in Neuromorphic to come up with more innovative designs. All right, so we talked about neuromorphic so far, but I would also say heterogeneity is really, really important. So again, there won't be just one neuron fits all. We might need diversity in our implementation. And that's really important, especially since our digital systems are really saturating in terms of performance. So I would feel free to read our paper. It's called Truly Heterogeneous Computing, and it's about some ideas about how neuromorphic and HPC systems can be made truly heterogeneous. All right, so now we're moving on to the second half of the talk, which is essentially, we were talking a lot about how do we design better AI, but how do we use AI while we're designing these systems? So this was some, I would say, like an interesting idea we had a few years ago, where we were essentially thinking, how about we put AI in the loop, where we specify all the constraints for our design. And so this is typically what you would see as a microelectronic stack. You have your applications and your algorithms, you have your system and your architecture, and then you have circuits, devices, and materials, most of which a lot of us don't even look at, right? Typically, if you're designing, most people sit at the application algorithm level, but you're not even thinking about what's going on in the hardware. But what if you had some help doing this co-design to specify the constraints that you need to design such systems? So we had this project called Coin Flips, and essentially a big driving factor for coin flips was the fact that we see a lot of stochasticity in the brain. But how do we leverage this for computation? And in particular, our application in this case was high energy physics, where they generate a lot of random numbers. And so the idea was, why don't we use these devices to generate two random number generators and use them for computation? Again, this was a multi-institution effort. And what we did was, we saw in this high energy physics applications, they were taking about 40 to 50% of the CPU's compute time just to generate pseudo-random number generators. And what we did was try to use our coin flips approach, which is essentially, typically when you generate random numbers, or pseudo-random numbers, I should rather say, you take your desired, you have your desired non-uniform distribution that you want, and you draw from a uniform distribution, you accept, reject, sample to get your non-uniform distribution, and that can be really expensive. And instead, our approach was, how do you actually directly construct your non-uniform distribution using these devices? But that was quite challenging. So what we did was we used AI in the loop, so to say. We used reinforcement learning as well as evolutionary algorithms to actually speed up this co-design. And so in evolutionary algorithms, we use LEAP, which is Library of Evolutionary Algorithms in Python. And for reinforcement learning, we basically trained it based on the PPO policy that came out of OpenAI. But what was the key difference is we provided it with the physics-based device models and the materials models that it needed for the low-level hardware while it was doing these designs. So in this case, we were able to do multi-objective optimization. So in this case, I have my objective for my application, which is I want the random number distribution that I want. So we had the Kullback-Leibler divergence, which is just basically telling you how close to the curve fit I am. And you also look at how close or far you are from a fair coin, because remember, we're doing coin flips in this case, zeros or ones, and that's how I'm constructing my bit stream, and then also looking at the energy. How much energy does it take per device? And essentially, we were able to use, in this case, evolutionary algorithms to kind of come up with this Pareto front, kind of optimal parameters that we would need to design for this algorithm. Now, in terms of reinforcement learning, we also wanted to try this as another algorithm. We did the same thing, but we had to define the reward function slightly differently. And we were also changing material parameters, which I don't know if there's any device person here, but that's another challenge in terms of coming up with design. So what was interesting in terms of training the reinforcement learning agent was it had two opposing objectives. It had to minimize energy, and it also had to minimize the KL divergence, which is how close of a fit I get to the distribution I'm trying to get. And essentially, as you can see in this graph, it struggled with it as it was learning. But essentially, based on how we weighted our reward function, finally, it optimized more for KL divergence because we care more about that particular application. We want our true random number generator to work as we want. And that was interesting because typically if I was doing this completely in isolation and I was building this device, I might have favored more energy in this case. But it's not that the energy number that I picked up was bad, but it optimized more for the task. And that's another thing that's really important as we're using these AI systems in the loop is how you define your reward, how you weight each objective would be important for us. And what was neat was our collaborator at UT Austin, they further showed why looking at these new devices is better because we're further going down in energy per bit using these novel devices while getting faster operation, as you can see in the green area. All right, so with that, I think I'm very close to the time I was slotted, but in terms of where next generation of neuromorphic architectures are going, the field is still really, really active. There are many, many drivers in terms of applications. There is certainly AI and machine learning. There's also a lot of interest in capturing more brain-inspired realism in circuits and systems, and I certainly think that's possible. So there's a lot of work to be done there. Edge computing is another really big application area that's coming up because people care about energy and performance a lot. Scientific computing is really great, and especially at Sandia, we care a lot about those kinds of applications. So some of my colleagues have demonstrated random walks using neuromorphic systems. Probabilistic computing, which was the coin flips example I was showing you earlier, but also high performance computing. And there's a lot of need in terms of moving past the limits of digital computing the way we see it. And I would almost argue there's plenty to do in analog CMOS itself. So again, to remind you, transistors are not just switches. They have analog behavior, and you can actually capture that efficiently in circuits. And in some ways, I would argue this will take not just algorithms, but really concerted co-design with the hardware, where you guys, mostly as CS majors, need to start caring more about the hardware that is underlying. And believe it or not, computer engineering and computer science used to work a lot more closely than they have in the past few decades. So I think we need to kind of reunite our efforts, if you will, in some ways to come up with better solutions for architectures and algorithms. And so I think with that, that's the end of my talk. This is our group's webpage, neuroscience.sandia.gov. We are a really diverse group of mathematicians, physicists, electrical and computer engineers, computer scientists, and neuroscientists. So it's I would say, one of the largest neuromorphic groups in the US, and with the most number of hardware that we have in the US as well. So please come talk to us if you're interested in this field. We're always looking for young and bright talent. So thank you very much. All right, questions? Please. Do you consider what did you say? Forward application? Oh, formal verification. Very good question. So for people, well, I guess for online, the question is, do we consider formal verification for our designs? I would say absolutely, because that would be in the co-design loop. Whenever your design is finally created, you need to check if that would actually work or not. So absolutely. So in this case, the example that I showed, the physics-based model, we had a different abstracted check because we didn't quite have the specific tool integrated into it, but that's absolutely the ecosystem we are trying to build, because formal verification is a very big part of you being able to tell if that will work once it's fabricated. So, please. So yeah, the question was why we use dendrites as a starting point in the pooling layer. Are there other layers where dendrites could be used? And what was the motivation? So generally, pooling layer, the simplest answer is it was the simplest layer to start with, right? And it's the simplest layer to show integration of inputs coming in. So that was why it was the starting point, but absolutely we want to replace all the other layers with dendrites too, because in my opinion, dendrites could almost act like dictionaries, if you will, right? So you have spatiotemporal inputs just streaming in really quickly, and dendrites can very quickly pick out the pattern, right? So in a way, it's exactly like what you see, these giant matrix multiplication that are happening right now, but you would do that in the dendrites themselves. And it would be like pretty quick as the inputs are just coming through. So that's what we are testing right now. That's work we're working on actively right now, and we're hoping we're implementing that in transformers. And kind of the shunting inhibition mechanism I was showing, we're trying to model attention in a different way. So if there's a different kind of input that can, veto a particular pattern that was generated or not, we could probably do something like attention modeling that we see in transformers as well. So there are other aspects of using the dendrite that we're absolutely working on. So that was just a good starting point for this. Yeah, so I think the closest analogy I have, and I'm not sure I have numbers for it, but so the place where we had the 256 hidden layer of neurons and we replaced it with 16 lift neurons with the dendrites, that was the obvious place where it would be very cheap. Now, if you think about a leaky integrated fire neuron, it look very similar to a dendrite in terms of the circuitry, except it has a thresholding component, right? And that can be very expensive in hardware. So when I implement multiple of those, it becomes very expensive. Whereas if I have a dendritic network where I'm just integrating the information and I'm having some leak along the way, so it's like a multi-compartment system, it's a cheaper implementation of the neuron as a whole. So hardware-wise, it was a lot cheaper without any hits to performance, basically. So definitely in terms of, I don't think it would make a difference when I'm doing it purely algorithmically. In fact, simulating the analog dendrites in algorithms would be more expensive in some ways because you have all these other factors to account for. But that's why I would say hardware is the algorithm in a way, and this is something we also see in the brain, where there's no real separation between, hey, that's an algorithm that's getting applied to this particular kind of hardware. It's co-designed, it's co-evolved. So the hardware is where you'll get the win with that particular algorithm as well. Become a lot more cheaper. Yeah, so the question is if we went to perceptrons to begin with because it was simpler or easier because it was not enough hardware. I would say absolutely that's probably a good starting place for why we did that. Also, dendrites were not really well studied early on. So there was what I would, at least I see in neuroscience literature, a more soma-centric view of the world because soma is easy to measure from, versus dendrites were not well studied either. So there was a bit of not having a lot from neuroscience at that time either. But I think there's an increasing community even within neuroscience looking more closely at dendrites and the complexity that they bring to computation in neurons. That's growing. So there's, some of that is there. But absolutely, I think hardware is also an issue. Because modeling these, even if I say multi-compartment neurons, would be costly. But the argument there is if we're only limited to digital, that's where we're kind of losing out because in analog, you're not separately maintaining a counter for your membrane potential, if you will, or what your leak is. It's natively in how you've implemented the circuit. So those types of hardware are not easily available. That is true. So I do think for the neuromorphic community, we need more reconfigurable kind of prototyping devices that people can easily have access to. And I completely agree that's not easily accessible, which is why it's a pretty big claim to fame that Sandia has so many of these hardware systems. But I agree that it's not easy to get your hands on for anybody. That can hold people back. I know. Please come reach out to me, and we love to have students over for the summer too. And UNM is an academic collaborator, an academic alliance collaborator with Sandia. So hopefully we'll have more fruitful collaborations with you all. So thank you very much.